I've got this conducting ring here. I've got this magnet. Remember, magnets have magnetic field lines. They go all the way through the magnet. They come out of north and go back through south. If I just let this sit here, I've got flux flowing through my circle here. The flux is coming out like this, flowing through, but it's not changing. There's no induced EMF. Changing magnetic fields cause electric fields. Changing electric fields cause magnetic fields. If B is not changing, nothing happens. But what if I move this magnet in closer? Well, then these flux lines will get denser and denser. So I went from having just a couple of flux lines to having more flux lines. So that means the flux is not only pointing in that direction, but it's increasing. The direction of increase is in the right-hand direction. Faraday's law says d phi dt is opposite of EMF. So that means my induced EMF points in the opposite direction. Well, what do we mean by points? Means the current's going to flow around this conductor in such a way to create a magnetic field that points in the opposite direction of the increase. So my induced B, it literally creates a new magnet here. My B induced must point in the opposite direction. Well, what kind of current would make a B that points that way? We got to use our right-hand rule. Remember, anytime something is curly, use your fingers to curl. Anytime something is straight, use your thumb for the straight thing. So B is pointing that way. My fingers would curl around like this. That means the current would flow around like this. So here's my loop. As I bring this magnet in, my current would flow around like this to oppose the changing flux. And that requires work. It's like it creates a little magnet here. So you're doing this, those charges start flowing around. You can't make those flow around for free. That would violate conservation of energy. You're pushing on this magnet, this new magnet pushes back on you. You got to actually squeeze these together. You can feel it in your hands. It's real. You squeeze it together and you're squeezing, and that's forcing those charges to go around. You're creating a current. You ever have those little handheld flashlights? You do this thing and it lights up a flashlight? That's literally what you're doing. You're moving a magnet through a circuit, and through that work, you're changing the flux through a circuit, you're creating a current. Lighting up your light bulb. What if I take my magnet here and I move it away? So now I started with a couple of lines coming out. As this magnet moves away, my flux density is going to go down. Now maybe I've only got one line coming through. So flux is pointing that way, but it's decreasing. So in which direction is the flux increasing? That's what we're always asking. Flux increasing in which direction? And you're saying, well, it's not increasing, it's decreasing. If it's decreasing and pointing to the right, then it's increasing pointing to the left. My flux is increasing in the left-hand direction. Faraday's law says the induced EMF will create a new field that points in the opposite direction of the increase. So my new field will point to the right. Thumb in the direction of the field. My fingers have to curl around like this. So my induced current would flow around like this to create a magnetic field that way. That's how we think about this in terms of Faraday's law. Lenz's law kind of states this in a different manner. Lenz's law says the new magnet that you create tries to stop you from doing what you're doing. So here's an alternate way to think of it, one that I like a lot better. So I've got my magnet, I'm pushing toward my loop here. These don't want to come together. Something is going to oppose me. Lenz's law says the new current tries to stop you from doing whatever you're doing. Well, what would oppose me? A different magnet here that looks like this. Try to stop me from doing what I'm doing. Which way would that point? Thumb points in the direction of north. My current would flow around like that. I'm done. That's the whole problem. I don't have to think about, well, which direction does the flux increase? I don't even have to think about the flux. I just think it tries to stop me from doing what I'm doing. If I have a north and a south, and I have my loop here, and I try to push this guy over, the new current is going to say, I want you to stop doing that. I don't want these coming together. So I'm going to create a little magnet here that tries to stop you. It doesn't succeed, it just tries. North going the direction of my thumb, my current would flow around like this. If instead I had my south-north like this and I try to pull it away, this guy says, I'm not letting you go. I want to stop you from doing what you're doing. So I'm going to try to attract you back. I'm going to put a north here to try to hold this south in. Thumb points that way. Current would flow around like this.